Hello everyone. So, welcome back to the Artificial Intelligence with Python. We are going to start in 4 minutes. So, let us wait for 4 minutes. Till then, you can have a look at the PPT. Today, I'm going to try different ways to, and today's topic will not be too much in the depth because it can get sometimes tough, sometimes easy, but I will try to help you in understanding this topic in a layman language, right? I hope you guys will get along well. So, we are going to start in 4 minutes. No hurry, you can get your pen and paper. So, this is our lecture 2. Lecture 2, uncertainty. What is uncertainty? We are going to discuss in a minute or two. So, like uncertainty is like probability. So there's like no problem in that. Like probability, you guys have studied probability in maths, right? It is in maths. So we are we are going to talk about probability and how the computer uses probability to like predict something that may happen in the future or like may happen right now, something like that, right? uh, so uh, so let me open the ppt, and I think we should start now, right? People will join as to go. Let me introduce you to today's topic. So it is our lecture 2 of AI with Python, uncertainty. So, what is what is uncertainty in AI? So, in the previous lecture, we were looking at knowledge. Yeah, right. Our lecture 1 was knowledge. So, in knowledge, we were using some knowledge that we had about the world, right? Those were like true facts, like they can be true or false. Like we had some facts about the world, and AI was for sure that those facts are like real and that it can perform and like infer things from it. But most of the time, uh, there's always some uncertainty. Like the thing is not 100% sure. We cannot say for 100% like it's going to rain in the afternoon, right? We cannot say for 100%. We can say that it is sunny right now. We know that 100%. That's a knowledge fact. But that it may rain in the afternoon or like in the evening, that is not sure for 100%. Maybe it may remain cloudy or like chilly or like windy, right? In the or maybe sunny in the afternoon, like hot sun. Yeah. So we need to make correct decisions where this uncertainty is there, using probability. So as I have told you, AI rarely has complete knowledge. So based on different things that is happening, we may like to know what may happen next. Like what is the probability of something happening. So now let us get it just like this image. See this image. There is like no reason like that I have put this image arbitrarily chosen from the net. This is a perfect example of uncertainty. Most of the time we know that there are trees, it is tropical, it is sunny, but I mean sometimes we know, right? But most of the time it is like foggy. We have foggy data. We do not know the whole thing, right? We can see it is hilly, but we do not know if there's a river down there, it is vegetation down there. It is like foggy, right? Now let us get into probability and possible worlds. So uncertainty is represented as a set of events. Uh, it is written in the PPT first line. So we are going to calculate probability how? Like we are going to calculate it through the world which we want, the world which we want upon all the possible worlds. Like this, like this is the probability. So this is world. It is it is the omega symbol, a Greek symbol, right? Every possible situation is called a world, right? And this big omega is like all the worlds. So this may be one type of world present in omega, like dice. So 1 upon 6 chance of rolling 1 or like 2, like they have equal chance. Most of the time things don't have equal chance, but right now we are talking about equal chance, right? So this is a possible world in a set of worlds, right? So uncertainty is presented. My pen is feels thick, right? Yeah, now better. Uncertainty is presented as a set of events, each assigned a probability, the likelihood of that event occurring. The possible worlds, possible worlds, every possible situation, in every possible situation is called a world, denoted by a lowercase Greek symbol omega. This W type symbol, right? Rolling a dice produces six possible worlds and one for each outcome, right? So to express the probability of a specific world occurring, it is denoted as probability of that world. Probability of that world, right? This felt better. Probability of that world, right? Probability of this world happening in all the possible worlds. So this is basic, like how is probability uh, uh, counted as, like how it is calculated, like situ- uh, possible situation upon a set of situations, right? A world in possible situations. Now axioms and probability. So these rules are non-negotiable, and every valid probability model must satisfy them, right? These are always true. These are four axioms here. Let us go through them one by one. First is bounded range. So it goes something like this. The bounded looks something like this. uh, it is equal to or bigger than or greater than the probability, uh, the probability of something happening is equal to or greater than 0, or uh, equal to or less than 1. So it will, if it is 1, then it is certain. That is the second thing. And it is 0, it is impossible, it will never happen. Like rolling a 7 in a 6-sided die, it is impossible. The probability of getting a 7 is 0 in a 6-sided die. So probability is 0. Now probability of getting a number less than 7 in a 6-sided die is 1, because 100% it will be less than 7, right? So it is 1. but some but it is not necessarily 1 or 0, it may be something between, like it is 0.7%. So much closer to 1, but uh, not certain, right? So uh, then sums to 1, like there may be like probability of rolling a dice. 1 is 1 upon 6, 2 is also 1 upon 6, and then 1 upon 6 for 3, then 1 upon 6 for 4, and then 1 upon 6 for 5, and 1 upon 6 for 1 upon 6 for what? 6, right? So all of them actually have 1 upon 6 probability. They have all the same probability, right? So if I sum all of the probability for 1, for 2, for 3, for 4, for 5, for 6, it will sum up to 1. So how does it go? Like it is 6, so no LCM needed. So like 1, 2, 3, 4, 5, 6. We just add that, it is 6 upon 6, which means 1, right? They sum up to 1, and it will always sum up to 1. Okay, all the possible worlds, like probability of something not happening is 0.2 and happening is 0.8. So if we sum that up, sum those up, it is 1, right? This thick one is not responding properly. So these were the axioms. These are non-negotiable rules. So summing probabilities. So a standard die has 6 equal likely outcomes. So probability of R equals 1 upon 6, right? So 2 dice produces 36 equal likely outcomes. Okay, so when summing 2 dice, the 11 possible totals 2 to 12 are not equally likely. Probability of 12 is 1 upon 36. Only one outcome produces it. And probability of 7 has 6 upon 36 probability. That is 1 upon 6 upon 36. That is 1 upon 6. That is 6 outcomes produce it. Right? 6 outcomes produce it. So it is not equal, right? But if we sum up probability of adding the value got from 2 dice, and we sum those up, and we sum the probability of getting those numbers, they will come to 1. So let us try out like yeah, so this is it now. There are more combination for getting 7 summed up, like 4 plus 3, like 4 plus 3, like 3 plus 4, 4 plus 3, same. It's not responding, right? Yeah, 4 plus 3, 3 plus 4, 2 plus 5 also equals 7. So like that, like we may also have more possibilities, right? There are like 6, like 1 plus 6, 6 plus 1. So then how to compute? Divide the number of worlds where the event occurs by the total number of possible worlds. Unconditional probability is belief in a proposition without any other evidence. Dice rolls are unconditional. The outcome does not depend on previous events. Like here we are talking about unconditional probability. Unconditional probability is the degree of belief in a proposition in the absence of any other evidence. That is, uh, something happening in one world does not affect something happening in the second world. Like we are rolling 2 dice simultaneously. Now let's imagine the first dice rolled up to be 4 or like 6. The first dice rolled up to be 6. Now based on that, what is the probability of 2 in the other dice? That is unconditional, because knowing the outcome of first dice, it does not affect the second dice. Like what will it roll? It will be 1, 2, 3, 4, 5, 6, 1 upon 6, anything, right? It is not related to this dice, so they do not relate, right? So getting the evidence for the first dice does not change anything for the second dice. That is unconditional probability. There is no condition changing anything, right? But if this was conditional probability, what is conditional probability? uh, Conditional probability, if this was conditional probability, it means that outcome of first second die is affected by the first die. Like we can take the dice example in the following, like we know that first die rolled 6. Okay, first die rolled 6, first dice rolled 6. So now what do you want to know is what is the probability of the sum of the both the value, the number we roll, add up to 12. What is the probability? So this I can roll independently in 1 upon 6 states, I mean in 6 states, and to get 12 as the sum of both die, we need 6, and out of 6 possible outcomes there is only one outcome where we roll 6. So we have 1 upon 6 probability of getting the sum to be 12, right? If so it affected that a little bit, right? So our so how do we say that our degree of belief, uh, uh, degree of belief in a proposition given some evidence that has already been revealed. So how much certain we are that second thing is true, knowing that first thing is true? How do we write that? We write that through probability of A given probability of B. Probability of A given B. So A probability of A given B. So what is it? So B is the evidence. B is the evidence, and A is the thing which we are trying to find, right? So we know if B is true, yeah, B must be true, right? Like given that B is true, what is the probability of A? Like see the examples here. Like we know that it rained yesterday, so what's the probability that it rains today? So like most probably the weather stays consistent, so maybe there is a little more probability that it may also rain today. Like if it was like it is cloudy today, so it is more probable, so it is more probable to say that it may remain cloudy because weather may remain consistent, like it is zero point 0.6 probability or like zero point 0.7 probability. So raining yesterday, you see how it rained yesterday, and it changed my thinking process to know that I was using it to know get the probability to think that if it rained yesterday, so using the fact it may rain today also, right? So it was based on raining yesterday, so that means it was conditional. Another thing is probability of disease, given that these test results came. We know that these test results are true and these are all the test results that came. So based on the data which we have, uh, we have a lot of data, right? So we want to know that what is the probability of us getting uh, flu or something when it shows like we are hot, right? Our temperature is hot. So we may be cold when we are hot, right? We are cold when we are hot. So knowing that we are hot, our temperature is high, it may mean that we are like we have a cold, right? It uh, that was an example. And now, how do we calculate probability of A given B? Um, we calculated it through this formula. Uh, so we calculate it through this formula. Uh, so dividing by Probability of B restricts possible worlds to only those where B is true. Where B is true. We divided by a probability of B here because we only want to take, because we know that B is true and we only want to consider the world where B is true. We want to ignore the world where B is not true, right? So we are going, like we are going to know that if first one rolled a 6, so what is the probability of getting sum of 12? So we are going to remove all the words where uh, B rolled 1, right? So we divide it by B. So we read this as probability of A and B. You may remember this symbol from knowledge, right? Probability of A and B divided by probability of B. So the equivalent forms of these are probability of A and B equals probability of B into probability of A given B, and probability of A and B also is probability of A into probability of B given A. So let us do an example uh, using this formula only. Remember how we calculated that summing up to 12? We perform this step only. Now we know the formula, we are going to realize how we use this formula, right? So probability of A given B, so probability of A given B, right? So probability of rolling a 12 equals probability of uh, uh, equals probability of sum to 12 and 6. Wait a second. So now we want probability of sum to 12 given uh, the first die rolled to 6. So let me write probability of sum to 12 given our first die rolled a 6. So 6. Okay. So our first die rolled a 6. We want to calculate this. Now possibility of 6 as B by evidence. B by evidence is probability of 6 equals 1 upon 6, right? So probability of A and B. So we are going to do 1 upon 6 probability 1 upon 36, sorry. Ah, 1 upon 36. So the probability of sum is 12, uh, and given that first die rolled 6 equals 1 upon 36. It looks like a 5, like equal 36 goes like this probability of this and this is this is uh, so now what we do, we are going to divide by probability of B, because we counted some worlds extra, that's why we divide, right? So 1 upon 36, why is it not reading? 1 upon 36 divided by 1 upon 6, because we want the B we want 6 only to get the sum 12. There's no other way, right? So we all know maths. 1 upon 36 into 6 upon 1, which is into 6 only. 6 ones are 6, 6 are equals 1 upon 6 is the chance. Okay. So this was basically conditional probability. Uh, now let me use a whiteboard because this is not reading properly. I'm going to use the PPT, but to explain you guys, I'm going to use the whiteboard. So let us get a whiteboard. We don't need this now. So yeah, if you remember this board from the generative AI class, we used this board, right? So let us get back to the PPT for right now. So now let's talk about random variable. So random variable, a variable in probability with a domain of possible values it can take on. Like a random variable has a domain of possible value it can take on. Like we, mm, I have to use this. I cannot just switch again and again. So like this, roll. This is a random variable. So we can roll one. We can roll 1, 2, 3, 4, 5, 6. For flight, flight can be on time, flight can be delayed, flight can be cancelled. So it can take on these possible values like 1 or 2 or 3 or 4 or 5 or 6, or like on time or delayed or cancelled. So these are the domain of possible values. This roll or flight, the random variable can take on. So a probability distribution assigns a probability to each value, like probability of rolling 1, probability of rolling 2. So it gives value. So in a probability distribution, we assign this value, like probability of our flight being on time is like 60%, like 0.6 is 60%, and probability of delayed is 30%, and probability of being cancelled is 0.1%, 10%, right? So what is probability distribution? uh, Formal definition. uh, Formal definition can be probability distribution, the place where a random variable can uh, probability, takes a random variable, sorry, a probability distribution takes a random variable and gives the probability of each of its value in a domain. uh, so we have a domain, and in it, like we have this written in it, like flight equals on time equals 60%, like flight equals delayed equals 30%, the flight equals cancel equals 10%. So a domain of values is present in it. Now in a concise way, we can use this vector, which is a sequence, which has a sequence of values. A probability of flight is the random variable. It is 0 0.6, 0 0.3, 0.1. So we know it, 0 0.6, 0 0.3, 0.1. We just need to know which these values assign to, whether it assigns to on time, to delayed, or to cancelled, and in which order. We just need to know that, and then we can just pick it up. Like we know that on time is in the first one. We are just going to pick up the first value and just put it in the on time. If we knew wrong, then it may cause problem, like we thought like this second one. So we may take 30% if we wrote wrong, right? Now comes this important topic of independence and dependency. This is a very important idea. So independence is the knowledge that one event occurrence does not affect the probability of the other event. Like an unconditional probability, it may seem like, right? So it is the knowledge that one event occurrence does not affect the probability of the other event, uh, like event A and B are independent, and if one does not affect the probability of the other, formally we can say the of probability of A and B. Now we know that A and B are independent equals probability of A A into probability of B. Like let me use this. Hmm. So probability of A and B equals probability of A into probability of B. This dot is into, right? Hmm. Probability of A into probability of B. Because there is no dependence. Both of them are independent, right? So like in the dice one, probability of first one rolling a 6 is 1 upon 6, second one rolling a 6 is 1 upon 6. So we multiply that with 1 upon 36, so the sum of coming 12 is 1 upon 36, right? It is not dependent. But if there is dependence, that is uh, that probability of B or like probability of A does change the probability of B, it directly affects it. Then it goes like this: probability of A and B equals probability of A, which we want, which we into probability of B, given that we know A. So I think we know A here or B here. Let me give you an example. Um, Here uh, I have given this example already, but dependence I will give you an example later. Like not independent, like another way of doing something like this is like one die is blue die and one die is like red die. A is red, B is blue. So what is the probability of rolling two red dice? It is zero. It means they are not independent, right? They are not independent. So just a second. Now where is PPD? Yeah. Remnants, morning clouds and afternoon rain influence each other, right? We are going to discuss that in detail. That's why I'm not discussing right now. Base rule. It is one of the most important things which we are going to learn. Let me check if it is reading my mic. Yes, it is reading my mic. We had some issue with the mic last time, so that's why I'm checking, right? Uh, so what is base rule? And before learning what is Bayes' rule, why do we use Bayes' rule? Let me tell you. Uh, Let me tell you that probability of uh, disease. Let's take disease. I don't know what to use this right now, so let me use. Let me come back here. Hmm. So Bayes' rule allows us that if we know the probability, let me go into a new page. That if we know the probability of some visible effect, given some unknown cause, given some unknown cause with Bayes rule we can calculate we can also calculate the opposite probability of the unknown cause given that we have some visible effect. And this comes in useful when you look at this when you look at this example. This is very important for a doctor because of a time we want to calculate what is happening based on uh, what has happened based on what is happening, but doctor always have the data related to visible effect given some unknown cause. So we all, if we have access to this, we want to be able to calculate the probability of unknown cause given visual effect, which is when a Bayes rule come into place, right? So this is Bayes rule. I will give you a nice example. Uh, I got a very nice example for this one actually. So how does Bayes rule? What does Bayes rule look like? Uh, the rule looks something like this: probability of A given B, probability of probability of B given A, probability of A given B, into probability of B upon probability of A. How? Uh, see, we are going to use that probability of A. I had explained somewhere, I guess. Okay, not till now. Actually, there is one probability of A. We know how to calculate the probability of A. Through that, we can also derive this. But here we can say probability of A in probability of B given A equals probability of B into probability of A into B. So this came from the formula which we just did uh, for calculating the probability. Is it back there? This one. The like it is similar to this one, right? So probability of A and probability of B given A. We have that on one side, and on the other side we have probability of B A, which we had. Hmm. Excuse me. Huh. Here. So probability of A even B equals probability of A and B upon probability of B. Now, thing is, the, the probability of A given B independence or like independence actually, sorry, independence can be written as something else. As I wrote, where did I write this? Ah, this is it. Here, this is dependence, right? So if this is dependence, and this is how we write this. We can just take probability of A and write it below this. That is how the rule came. So probability. So here, let me tell you how we derived it. Probability of A given probability of B equal probability A. I'm going to write this somewhere nice where we have space. Or let me just create space. So let me write here. So let us first look what is our goal. Our goal is getting the Bayes rule, which looks like probability. Sorry, uh, which looks like oh, which looks like probability of B given A equals probability of B into probability of A given B upon probability of A. We want to know this, and we are going to use this plus the dependence. So we are going to write probability of A and B equals uh, sorry, A equals probability of A into probability of B given A upon probability of B, which we have. Probability of B can go with probability of probability of, now this can go here. So probability of B into probability, it was dividing here, so it will multiply here. The probability of A given B equals probability of A into probability of B given A, and B given A, and we are just missing a probability of A, which will go here, and we will write this same as I've written here, and we have successfully derived Bayes rule. Okay, did you guys uh, did you guys understand? Did you guys understand? I wish you guys understood. So let us get back to the PPT. I'm getting too much into the depth of how we derive formulas. So let us go a little faster. Let us do a small example. We are going to this. We are going to do this one fast. Okay. Uh, Not hurry. Just we are not going to waste time. So let me dictate this to you. Listen very carefully. Let me just open the PPT. Well, I have I have the answer here. So let me just go back then. Don't see it. Okay. Let me give you a question, and then we are going to have a look at the answer. So the question goes like this. Given cloud in morning, I repeat. Given cloud in morning, I would like to see you guys. Given cloud in morning, what is the probability of rain in the afternoon? Given that we know these three things, those three things are 80% of rainy afternoons start with cloudy mornings. Okay? And then 40% of the days, second thing, 40% of the days have cloudy morning. Then 10% of the days have rainy afternoons. Okay? I want to repeat. Given cloudy in the morning, what is the probability of rain in the afternoon? Given that 80% of rainy afternoon start with cloudy morning, that is probability of B. Then 40% of days have cloudy morning, that is probability of A. And then 10% of days have rainy afternoon, that is probability of A given B. Okay, so this is the question. I hope you guys heard it. Now I have solved this, and hint, use the Bayes rule, please. Use the Bayes rule. Let me get back to the PPT, and let's have a look at the answer. The answer goes something like this. I'm in probability of A. I mixed up one thing. Probability of cloud given rain is 80%, not probability of B. Okay. So, so it goes like this. Where's my pen? The Bayes rule. looks like this. Hmm. It looks like this. Probability of B given A equals probability of B, let us hurry. Probability of A given B upon probability of A, that is the Bayes rule. Now we are going to fit the evidence which we got. Uh, Probability of B into A given B upon probability of A. Okay, now we just need to calculate this whole thing. It goes like this. It goes like this. Um, and then we go 0.2. So we have 20% chance, for 20% chance that we will have a cloud in the morning. I mean, given cloud in the morning, we will have rain in the afternoon. That is a chance. Given that rain in the morning, rain in the afternoon. Given that we knew that rain in the afternoon starts with cloudy morning, that is 80%, right? So we have 20% chance. Not fairly good chance, but okay chance, right? Now let's get into joint probability. Joint probability is probability of two things together we are calculating, right? So like cloud and rain we are calculating together. This may seem a little not too easy to understand. Sorry, not too easy to understand, but it is easy. Don't get afraid. It is easier to understand this in a table. Let me draw you some tables. C equals cloud, okay? And dot C equals not cloud. I mean, not C equals not cloudy. Probability of cloud is zero point 0.4 and probability of not cloud is 0.6 in the AM. And in the PM, we have R equals rain, okay, and not R equals not rain. You know this symbol. We did this in the knowledge one. You can go check it out after this class. Probability of rain is 0.1 and probability of not rain is 0.9. And now we want joint probability distribution. It looks something like this: C, not C, R, not R. Probability goes like this: 0.08, 0.88, 0.32, 0.02, and 0.58. Some of them is 1. You see, I mean, some comes out to be 1, right? Some needs to come out as 1. All of them, all of the probability. These are 4 possible worlds, right? So now we can use this table to know probability of cloud given rain. Uh, how do we calculate that? Probability of cloud given rain is probability of cloud given rain. We can just see here 0.08, right? So the probability rules: conditional, marginal, cloud rain, and marginal. Uh, uh, Margins alone cannot reveal if C and R are related. Joint table encodes all dependencies, right? This is it. This is the vector, the alpha. Probability of rain can be removed actually. This thing. This thing. Sorry. Uh, I don't want to try that. Yeah. Probability of rain can be cut. It is not working. It is not responding today. I don't know why. Not here. Cannot be cut here. When we write and C or like only comma, and then we can put alpha, the alpha which is here, and then C and rain. Where is it? We had the distribution. I have it written here too. I do not need to change here. So we wanted cloudy given rain. Cloudy given rain. So that is 0.08. But there's another table. This is from another table actually. This is from another table. That table we can leave it for now. This example was only for explaining joint probability. Oh, you guys also want to do the this one. Let's leave this for now. It is very easy. We just use probability of a probability of a and b upon probability of b, and then we cut this. We add alpha. Alpha is just to normalize the values. Uh, that is the probability of a and b. We from that table we knew that it was this and this. So alpha came out to be this, and then we normalized it through alpha. Alpha was 10 because we wanted this was 8% 2%. We made that 80% 20% to make because we want the sum to be 100% because 1 equals 100%, right? That's why we use alpha, and then we got our answer. It is vector. Okay, nothing is useless. It is also important. That's why I told you a bit. Four core four core possibility rules. The four core possibility rules. Uh, the four core possibility rules. Okay, the four core possibility rules are negation, inclusion, exclusion, marginalization, and the fourth one which we have here is conditioning. We have conditioning too. I have conditioning here. Let me explain you the rules. The rules follow from the anxious of Paul's actions. So, you guys want a break? We will do the break after this whole possibility rules 5-minute break because we are going to start Bayesian network after this, right? So we are going to do a break of 5 minutes. First is negation. First is negation. So probability of not A equals probability of 1 equals probability of 1 minus probability of A. Just a second. So just a second, guys. Can you wait a second? So let's continue. Negation. Probability of not equals 1 minus probability of A. That is complementary events occur all possible worlds with sum to 1. So we know that if it is not occurring, so probability of not A will be 1 minus probability of A. That is basic maths, right? Then let us get into marginalization, I guess. No, inclusion, exclusion first. Inclusion, exclusion. Subtract the overlap to avoid double counting where both A and B are true. Let me open this. And to explain this here, yeah. So, what was the inclusion exclusion? Probability of A or B. They are either one of them. So, probability of A, we know is or symbol for probability of A plus probability of B minus probability of A and B. So, this is for inclusion exclusion. So we want to know probability of A or probability of B. So both of them cannot be majority, of course. So we want the worlds where probability of we want a probability of A and probability of B. But we subtract the world where probability of A and B is true. We subtract that world to get probability of A or B. We know the probability of A, we know B, but we know that both cannot be included. So that's why it is or, because both are not there, or A or B, right? That is inclusion exclusion. Then let us do marginalization. We have two forms here. One is boolean, as it is true or false, and one which is not boolean. Okay, let me show you here. I think we have written it here. This is a boolean one. This is a boolean one. So uh, sum over all values of B, since B and not B are disjoint and exhaustive. Okay, we want probability of A. One way, this is one way of getting probability of A, right? This is one way of getting probability of A. It is probability of A equals probability of A and B, this comma is and, okay, plus probability of A and not B. So in the joint distribution table, we have all those connected A, B, A and B, A and not B. We all have all of them connected. So we are going. So so here when this is used when B is boolean, either true or false. So we can get probability of A, right? So we want I have that, right? So probability of uh, R R is like probability of R and C and R and not C. So we add both of them and its probability of raining is like 10%, right? Here, right? It worked, right? That is why we use this, because we know how to calculate that. We want the computer to know that. Now, what if it is not boolean? That is the last thing which we will cover before a break. Because it is a long topic, it may take another hour, of course. Yeah. So, pen. This topic is known as marginalization. I'll write that for you. Marginalization. That looks a little off. Okay. Yeah. Marginalization. This was marginalization. Now, what if it is not boolean? Yeah, sorry, forgot. Got it off. I was telling you, what if it is not boolean? It looks something like this. Probability. Don't let me write this first, then I'm going to explain. Don't get scared at looking at it. It just looks a little complex. It is the same idea like a previous slide. This comma equals this had to caps, sorry, that matters actually, because caps sorry, we're not using that, we are using this, we're using internals. So this caps mean the whole world, all the possible ones. why I'm not able to select. Yeah, selected y and yj and close. This is marginalization rule when b is not boolean. You say there's no b, a and b are replaced by x and y. Okay, so probability of x, probability of a, you can say, let's say probability of x here, probability of x equals something in x is sum of all ranging over all the possibility j, the possibility of x equals xi, that is possibility of a, and y equals yj. So you, so yj, and we want to sum that. So uh, yeah, so you can use it here. Like we want sum, like we were saying before, and we were doing it for all the b's, like b and not b, they were b and not b, but if they are more than one, because it's not boolean, right? So all the b's, that is y's, so j, y, so how many words are there, it is denoted by j. So we want those and we want the sum, right? We will get those from the distribution table, all the x's and y's and their possible words from the distribution table. We're going to add them, all of them, range over them, and add them, range to find all of them, and then we are going to get x, right? Probability of x. I have already given you the example, no need for again. Conditioning is left, that is your conditioning. Yeah, conditioning. Conditioning looks like this. Probability of a equals probability of a given b into probability of b plus probability of a given not b and probability of not b. Last one was not dependent. This one is dependent because this is conditioning. Another way of writing this, if b is not boolean, is x equals xi equals sum j again. It looks similar, but this time it is conditional. It is not independent. So we know that y is true, right? This time, so we are going to count that, and then we want uh, sum of probability of a and b and a and not b, right? Probability of a and b, probability of a and not b, b and not b complementary, b and not b complementary, b and not b complementary, a remains, and we are going to add them, right? So this is conditioning. We are not going to get into much more harder and different rules. There are many more like these. So we are going to weight each conditional probability by the pair of b. Okay, that is more formal. Now we have a 5 minute break, guys. 5 minutes break. Before we start Bayesian network, you can have a look at it. But I think you guys may need a 5 minute break, and so do I, because these topics are not so easy to grasp. So I'm going to give you a minute so that you can have a look at it and like have a little bit of fun or something. Or I mean by fun, think like where is this useful, right? So thank you for the support, guys. uh, 5 minute break, 5 minute breaks. I'm going to write it here. I like using new slides every time, right? 5 We are going to turn on 34. Okay, 1 minute has already happened. 5 minutes break. That is official. But we have it on recording, of course. So 5 minutes has officially started. Go have a sip of water. If you, if I suggest you should keep a water bottle with you, water bottle, right? Go have a sip of water. Next thing which we are going to study is Bayesian network. Bayesian network. In that we only need to know relationships, condition probability, that is, and the disjoint probability. There's nothing else. Then we are going to do inference by enumeration. Like we are going to have a query variable for which to compute distribution, and we are going to have evident observed variable for event E. Then we are going to have some hidden variable too, non-evidence and non-query variable, because right now we only have two variables, right? Now we want some hidden evidence too. Maybe we have some hidden evidence, not always. Maybe it is a non-evidence, maybe it is a non-query variable, and then we have a goal to calculate probability of x given E, right? It goes something like that. Probability of x given E equals alpha into probability of x and E equals alpha into sum of I into probability of x, E and Y. It is very easy. E is the evidence, x is the query variable, Y is the range, and A normalizes the result. Well, we are also going to study optimization of all this, and optimization of all this like through sampling, and then after sampling they are also going to optimize sampling too, and then we are going to get into uncertainty of time. So today's session will take a little bit of time. Yeah, uncertainty of time too, we have to study. And then we also have to study the hidden Markov model, which we are going to study with the t of course time period. Okay, I will give your mind a rest by 2 minutes silence. There is no way to mute ourselves, is there? I have no idea. Well, till a break is there, I want to talk about knowledge culture. Knowledge culture is like new, but its intentions are not new. In this market, we are not trying a way to give. I'm not trying a way to give strategic positioning, but I'm trying to tell you about our analysis. I mean, our mission, our objective as knowledge culture. As knowledge culture, here we want all of you to study new things, tech. We are focused on, right? We are focused on that small segment. It is growing a lot, right? There are new things every day, and we want you to know of them. We have a special focus on AI because we are trying to get artificial super intelligence. For those of you guys who do not know artificial super intelligence, that is why we want to teach artificial intelligence. Right? Artificial nano intelligence have passed. Those were weak AIs. Now we are in artificial general intelligence. Right? We are going through that stage of AI where AI can take human decisions. Right? But we want it to do something which human cannot. Like we want real help like that. That is artificial super intelligence. When it is super intelligent. So our mission basically is to teach you guys, or at least artificial general intelligence and narrow intelligence, to make you guys ready for artificial super intelligence, right? Also, we want you guys to be knowledgeable in the terms of AI because it is a very growing big sector, right? And other thing can be that artificial intelligence is no joke, right? Artificial intelligence is an opportunity. If you guys say artificial intelligence is taking a lot of jobs, yeah, it is taking some, yeah, AI agents are, but that is actually not true. I'm ready to fight over that, guys. You can talk to me about that, right? With artificial intelligence in your brains, I also want you to teach how to use artificial intelligence, like prompt engineering, what tools to use, right? So, like toolkit masterclass. So, we can get into that sometimes, but I have a plan to of another artificial intelligence lesson on a very basic level. This is a very high level, college level, I can say 10th, or some of these things are there in 10th grade, but most of them are in college. Yeah, for the schoolers, the scholars, I mean the learners who are in school, I also want them to know artificial intelligence. So that's why I teach such in a layman language and take so much time, right? See, Python is not the specialty of merge culture, but we are also trying to get into other things like Azure, Python, coding, right? And also into vibe coding. It is a part of coding like using artificial intelligence, like yeah, using Aniden and all, right? We may even give you an automation masterclass, right? But that is the plan for later. My plan for right now is to start a very basic artificial intelligence course, like learning from scratch, like you are learning from start. Like, what is data? Do you guys know what is data? We use data every day, right? But many of you guys know what is data, but you are not able to express it. I want you guys to be able to express it, right? I want you guys to know what is data and how to use that data, the different domains of AI, the different ethics of AI. We will even get into the ethics and the work opportunities with AI, right? That is only possible through a very basic course in which we are going to learn all of this thing from scratch, and the classes are not possible for every day because I also have a busy schedule. Yeah, but if you guys want a course like that, message me, comment, or I may even do a poll. We will see. It is 4:40. Let us not waste more time and get into let us now get into artificial intelligence and let us continue this. So, Bayesian networks. What is a Bayesian network? A Bayesian network is a directed graph representing dependencies among random variables, right? I mean, not a right place to say right. I mean, you know, a Bayesian network is a directed graph is representing dependencies among random variables. Each node is a random variable, right? I mean, an arrow from x to y means x is the parent of y and y's distribution depends on x. Each node x stores a probability of x given parent parent of x, right? This example you see here, let me draw this for you. I don't want to read this, right? I want you to visualize this, and this is going to be very easy if you guys stay along, stay consistent, in artificial intelligence, of course. We can do this. Bake is over. Let's finish it. Hmm. Bayesian network. I have a direct graph right here. This is approximate. I read the general. I already read the youth general definition. Let me draw this directed graph for of this random variable versus rain, and it may take none, or maybe light rain, or maybe heavy rain. Then we may have track maintenance. I'm just going to write M for maintenance. Okay, that's usually in short forms, and there can be yes, there is track maintenance, and no, there is no track maintenance. And then there is this thing which is connected on both maintenance and rain. What is that? That could be our train, because it is on a track. If there is maintenance, there is a possibility of delay. T train, it can be on time and it could be delayed. And then appointment is directly influenced by the result of train, so we can attend the appointment or we can miss the appointment because of the train outcome, which whatever it takes for, like delayed or on time. So this is a Bayesian network connected of random variables, and we have a lot of distribution table connecting all of these. I do not want to create the whole table. It is going to waste time. Let us get into uh, what really it is and how can we use it. Right. So, alright. Now appointment is influenced from maintenance, but we want direct relationship. And given that I know that train variables, that the train variables probabilities uh, based on maintenance and rain, of course. The maintenance, I can just distribute them based on collected data on train for the appointment, right? So now how to compute these joint probabilities? Like we need to find probability of light rain, no maintenance, and delayed. How do we write that? Because these are conditional. T is equal to probability of light because it has no parent, it is independent. Then there is into probability of no maintenance given light rain into, let me take the next line, into probability of delayed train given that we have light train and no track maintenance. And then take our we just take values from the joint probability and we fetch them and we put them here and then we multiply, right? Same can be done for finding the appointment. If it is like light, no rain, delayed, and also miss this time. We go to the previous board, same thing, but now we are also going to add probability of miss given delayed. We are not going to write the whole thing because I told you already. We want for the miss one, we want more direct relationship. Like if there is maintenance but train is still on time, like there's maintenance, so there is a possibility that train is not on time. But let's say there's maintenance and train is still on time, then there's more probability of appointment being attended, right? So if I calculate maintenance too, it may impact, right? It may impact a little, right? So I told you we want more direct relationships. So given that I know the train's variable probabilities based on maintenance, I can just distribute based on collected data, like on train for appointment. Like all time attend will be 90%, on time miss will be like 10%, delayed attend will be like 60%, and delayed miss will be like 40%, something like that, right? Now let us get into inference by probability. Inference by probability is what I was telling in the break. Don't get scared. I mean, don't think like, huh? He was teaching in the break. No, I was not teaching. I was just discussing what he will study. So, what is inference in probability? We have four things. First is the query x, right? That is the variable which we want to compute. Then we have got this evidence e, evidence variable, e, maybe, right? And then we may got a hidden variable too. Hidden evidence, I mean, hidden evidence. It is also an evidence, but it is hidden. Like denoted by. It is like non-evidence, non-query variable. And then we have our goal. And goal will always be to calculate probability of x through the hidden variable. Oh shit. Hidden variable. Given that we know the hidden given the hidden variable. Like this. We're going to use some instance rules, so remember those, get those in your mind back. Query goes like this. Probability of appointment given light rain and no track maintenance. We do not know train here, okay? Train is the hidden variable. So, sorry. Yeah. How do we do that? Alpha to normalize probability, appointment, light, and no maintenance. Just how we do that using probability of A given B equals alpha and probability of A and B. Then we are going to use the what do we say marginalization now. So now we are going to say alpha log once probability of appointment, light rain, no maintenance, and on time. And this is not boolean, this is like two different things, and plus probability of appointment, light, no maintenance, and delayed. We take both of the values that can be taken possible, and then we just put the values, and we just this is as far as we can go. Now we just need to calculate this, right? So this is where we stop, and now let me show you this. This is what we did in a more general way. This is known as inference by enumeration. Probability of x given e, a query equals alpha into probability of x and e, and alpha Then we are going to sum that thing up. Range over values of hidden variables. Sum of probability of x, e and y. All the hidden variables will be there. Right. The hidden variables were light and not maintenance. I think so. This was inference. X is the query variable, E is the evidence. Y ranges over all the hidden variable and A normalizes the result. Now what is the problem with this? Can you guys guess? I wish you guys can guess. But let me tell you if you cannot. This is not optimal in case of many numbers or variables taking time and computation. What if there are many things for train, right? On time and delayed. That was our hidden variable actually. Confirmed. So on time delayed. We have only two. What are there? We have a lot, right? As a human, we don't need exact probability. Not dealing the solution. We don't need the exact probability. As a human, I do not want to notice like 0.348 or like 0.03. We just want to know, yeah, more likely, less likely, or like average, like 10% chance is not going to be there, but 3.4% chance. Like, you know what? Exact. We want certain, not certain. I mean, more certain, less certain. So why do we do all this computation then? Let me introduce you to sampling. How much time? We have been doing for 1.5 hours. Okay. Sampling. Sampling goes like this. Let me go back to our Bayesian network. Here it is. And now let me introduce you to the steps. No, not erase all. Not this eraser. I wanted this eraser. This. No need of this. So, what do you think, guys? What do we do? What do we do? I said sampling. We're doing sampling. So, based on the name, what do we do? What do we actually do in sampling? Not as per this. Normally, when we do sampling for anything, sampling is like taking a sample and then trying that, taking different sample, different types of combinations to the samples, right? So let us take a sample. Let us create a sample. We are going to choose arbitrarily from range. Let us say we choose none. So r equals none. Then maintenance equals yes. Then if there is no rain, then like let's say it is on time. And then appointments, let's say attend. We are going to take all of the possible samples, like pick for arbitrarily, then I pick other options and then get combination of samples. This is one sample. We want thousands, 10,000s, 100,000s, lakhs, crores, millions samples, right? Now let's say I have 8 samples, just 8. Of course it will not be accurate, but let's us say that we have 8 samples. And someone asks, what is the probability of train being on time? Now I check all the samples which I have, 8 samples, and Let's say out of 8 of them, out of 8, 6 samples out of 8 in the probability distribution uh, had that, had on time. 46 upon 8. Simplify that, and whatever you get, 3 by 4. It is not accurate, right? But all of the samples I have got based on all of the probability distributions, all the samples, all of the samples I've got, and this distribution table I have created the samples. I'm going to look and get. I'm going to fix train on time. I'm going to find train on time. How many train on time are there in all the possible worlds, right? All of the sample is one possible world. So how many possible worlds on time was there? And then we are going to do the same thing, world upon big omega, right? Omega upon big omega. So this was basic sampling. But there is also one more problem with sampling. Guess it, guys. Guess it. If you said, if you said that evidence sometimes can be very unlikely to happen, then I have to remove many samples. Remove many samples? What do I mean by that? In a sampling type, we have a sampling type of uh, what do we call? Rejection sampling. Rejection sampling. And we reject all of the worlds where probability of A and B is not true. We remove all of them. But what if B was very unlikely to happen and only happened in one case? So out of 100, only one time B happened, and we want the one in which B happened. So I have to remove 91 samples. That is too much work, right? It's very unlikely. So to solve this problem in rejection sampling, we have got this thing called likelihood weighting. What is it called, guys? Repeat after me. Hello, guys. Um, Shubham, I'm right now in likelihood weighting. You can start from beginning. I cannot start from beginning because we are already in 1.5 hour session. But we are studying probability, right? So we are right now studying sampling, and now we are studying likelihood weighting to solve the problem in likely to solve the problem in rejection sampling, right? So you will get it along the way. Uh, I will teach the things which are related, right? I'm not going to be like uh, going ahead. Uh, I am also going to teach what happened, why that happened. So why that happened was told a little earlier. So why that happened was told a little earlier. So I'm also going to tell why I did all of that, prediction sampling, what rules did I use. Those rules were explained earlier, but because I'm going to use the rules again, I'm going to explain those again little bit. So you will get along properly. There is no problem, right? And you can also check out other sections if you want more clarity even, right? So likelihood weighting. So first, we are going to start by fixing the value of the evidence variable. What is the evidence variable? This variable. I've written it here. See, I'm going back in the slides, is no problem, right? evidence variable, we are going to fix it in the sample. What is a sample, Shubham? A sample will look like this, and we are going to fix the hidden variable. Let's say this is the hidden variable. We are going to fix on time. Okay. Now we are going to sample the non-evidence variables using the conditional probabilities in the Bayesian network. Conditional probability, it is in the joint probability tables. Tables are not made, and I'm not getting too much into tables because tables are large, right? So using that, I'm going to create the sample. I'm going to create a sample which has low probability also and which has high probability also. The surrounding non-evidence variables. And what is the probability of then R, M, and A given with that we know T, like let's say it is zero point 0.6. So this sample is going to weigh zero point 0.6, right? Now if I have 8 samples and someone asks, I check sample and like I check samples and let's say 6 samples out of 8 and the probability uh, absolutely approximately based on sample. This is already told. Likelihood weighting, yeah. This I have to tell you, right. So first step was fixing, then using the probability. I got around with other samples like using the distribution table, and then I the distribution that came, I mean the value which came at the end was the sample value. So then we are going to arrange them in all the value, and then we are going to see which one is weight more, which one is weight less. It will, it may not seem necessary, but it will actually help you in the long run. Okay. So uh, now let's get into our last topic for today. Let us get go through the PPT first. Bayesian network done, right? Inference by Bayesian network done. Building the Bayesian network is not done. We are going to use the Python library, pomegranate library, right? And then for the root nodes which have no parent, we are going to use discrete distribution, and for the conditional and then we are going to use a conditional probability table for nodes which have parents, right? We're going to give every combination of parent values, and the parent distribution is passed in as a dependency, linking the graph structure, the arrows, right? Um, then we can pass in a query, and then we can just check it. If we want like joint probability, pass single observation to model not probability to get probability of like something, and like we give like no rain, no maintenance, no on time, and attended. But if we want like distributions given evidence, like a call model dot predict underscore the probability or train equals delayed. We want the probability of that, so we need to run the inference by enumeration, right? So we need to fit the enumeration coding into that, where we are not going to get into that. Then sampling, I've already told you. Is there a code? No, there is no code in this. Here is the code, how they generate a sample. So this is a simple code. This code follows step by step the things that I told you. Stop the video. Stop this video and take a look at it. We have got a function call in there, a sample and parent, and then for state in all the state, for state in model dot states, we'll look at the distribution table, and we are going to like choose arbitrarily, and then we are going to look at the distribution table, and then we are going to get all of the others. We're going to try different variation, different combination, and then we are going to return those samples. And then this is rejection sampling. Already told you rejection sampling. Likelihood weighting, I already told you now. There's nothing in likelihood weighting. Fixed evidence variable values, don't sample them. And then sample non-evidence variables from their conditional distribution. Then weight each sample by the probability of the evidence occurring. Example, no need. That is the same example actually I told you, the 0.61. Right. Yeah. Now we need to go into the Markov models. What is the Markov model? Why do we use Markov model? See, this is the last topic. And what did I tell you the last topic was in the break? Don't worry, don't worry. It was uncertainty of time. Till now, we were dealing with probability at the time and data with fixed things. But over time, the value of these might change, right? Then what do we do? For that, we need to add a time period. For example, I know that uh, there are sunny and rainy days. I don't want to know probability of rainy now, but probability, tomorrow, like it is rainy tomorrow or day after tomorrow. So for that, we don't say it is cloudy in the morning. So it was cloudy in the morning. So what it is right now? You can say it was cloudy yesterday. I mean today. So what will be tomorrow, right? To do this, we need a random variable, not only for the weather, but for weather over time, like weather plus sunny plus today, and another for weather plus sunny plus tomorrow. For that, we need time steps. We need time. Let me first get the heading. For that, uh, 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 uncertainty of time. So, um, where was that? So now we need to, for that we need to add time steps, like x t. Weather, just kind of like weather at time t. It can be a days, week, I don't know, right? Anything. Now I want to predict it for tomorrow, but then it could be based on the last 365 days. Like based on last 365 days, what is the probability of raining tomorrow? That is too much computation data. It is very tedious. So we want some assumption that something about the world is true. We want some assumption, and that assumption is known as Markov assumption. What I'm saying? A Markov assumption. What is a Markov assumption? Markov assumption is in the PPT. I guess. I guess it is not. These are all chains. Assumption is not there. I mean, it is there, but here it is. Yeah. So this is the Markov assumption. Markov assumption uh, is like the assumption that the current state depends only on a finite fixed number of previous states. Like we are only going to process the last 3 days, so like the last week or like the last day, like yesterday only. Now, uh, we do not have hundreds or thousands of previous universe days and its data. We have like past week, the trends of the past week, because trends change over time, right? You just cannot look over time. We are not sitting here explaining our computer what is trends. We are explaining it. We are trying to get the probability. So, what is the Markov chain? Markov chain is a sequence of random variables where the distribution of each variable follows the Markov assumption. Let me repeat. A sequence of random variables, let it repeat slowly actually. A sequence of random variables like sunny, rainy, uh, where the distribution of each variable follows the Markov assumption. Like it was not based on the last million of years. It was based on last 3 days. That's the Markov assumption, right? Markov assumption could have said like this on past week. So it would have said, okay, um, each variable will follow Markov assumption of last week. By last week I mean the trend in the last week, right? Now, like in the search algorithms, if you guys do not know search algorithm, check the first lecture, the lecture 0 of of, of our course, live session course, artificial intelligence with Python, search algorithm. It was our first one. In that I explained you transition model, uh, which we are right now going to use in search algorithm. We use that. So let me use that again for Markov chain. Now this transition model is a distribution table. It specifies the probability of the next state given the current state. Right? We know today, we want tomorrow. We do not want we know yesterday, we want today. We know today, we want tomorrow. Right? So we know today, we know today, we want the probability of tomorrow. Right? The next stage given today. Let me show you how they look like. So a transition model may look like this. Today, tomorrow, this is xt, and this is xt plus 1, because plus 1 day, and sunny, rainy. This is rain, sorry, not drawing properly right now. This is sunny, and then this is rain, poor rain. So today is sunny, tomorrow is sunny, chance 0.8. Today is sunny, tomorrow is rainy, chance 0.2. Today is rainy, tomorrow is sunny, chance 0.3. Today is rainy, tomorrow is also rainy, chance 0.7. This is a transition model, right? This is a transition model. And what is the Markov chain? It is like sunny, next day, also sunny, next day, it was raining, next day, it was also raining, and next day, it was also raining. This is x0 maybe today, and then based on that we got tomorrow, day after tomorrow, and day after that, and day after that. This relies on knowing the condition today, and we can predict another for tomorrow, right? But oftentimes the AI does not know. Okay, this is another thing. This is another thing I'm getting into now. Let me first check the PPT, right? We do not need to go off track. This is Markov chain. Let us first see the code. Again, we are going to use the pomegranate. Then there is the discrete distribution, right? And we are going to start with 0.5, and then we are going to give it the transition model, the conditional probability table, and then based on that we are going to start transitions, and then we are going to print the next 50 days, right? We are going to print the next 50 days like it is sunny or like rainy, and output will come like the chain I showed you, like next 50 days, like this is only 5 days, but it will come for like next 50 days, like sunny, sunny, rainy, rainy, sunny, rainy, rainy, sunny, sunny, right? So now with this So let's get into another problem in Markov. That is, oftentimes AI does not know its surroundings. Like it does not know outside. Like it is sunny or rainy. Today is rainy or sunny. It just have some sense. Some sense. Like some sense. And how does it have some sense? It has some sensor model. Like let me do you to some sensor model. The sensor model. Huh. So like hidden state, it is the surrounding, and what it knows is the observation. So based on the observation, spelling mistake, observation. So based on the observation, it tries to identify the hidden state. Let's say a robot's sensor data can tell uh, the robot's position, right? I'm correct, right? And another thing can be audio wavelength. It is observing some audio wavelength. You guys know what is wavelength? Okay. So it is the length of the crest. And, I'm not getting into physics. I mean, it is part of physics, right? Yeah, it is part of physics. Uh, the hidden state can be that words are being spoken. This is for Alexa, right? Another can be analytics. Analytics of a website, like app analytics or website analytics. The sensor, the hidden state can be some user engagement, some type of user engagement, right? So this is observation only. There is observation because there is some state. Like Alexa doesn't really know exactly what have you spoken actually, but it has observed some audio wavelengths, right? And now it has some task to do with using those audio wavelengths to find its state or like the words spoken, right? Example which we are going to use right now, very important example and very fundamental example: the hidden state and the observation. We observed use of umbrella. What do you think, guys? What is the weather? I mean, I give you the answer. Observation is like use of an umbrella. So the hidden state is weather. It is not sunny. Weather is the random variable. It can be sunny, it could be rainy. A use of umbrella could mean rainy, right? There are also types of umbrella. There's like some chance like it works for high heat. Yeah, right. So if we are observing use umbrella, the AI comes to know I am an AI who is observing umbrella. With umbrella, what can I observe? What can I know about the real world? I can know about the weather, like it is raining, like right. Does that make sense, guys? Right? It makes sense, right? So now let us get into Markov model, but not only Markov model, but hidden Markov model. What is a hidden Markov model? A Markov model for a system with hidden states that generates some observed event. Uh, the sensor model. Let me write the sensor model for you. The sensor model can look like this. This is the observation at that time, many times subsidiary. And this is the state that must be at that time. See, there's no plus because we have observation of that time only. And then we have sunny. because we know the state is umbrella. State is an umbrella. Sorry, state is weather. So weather can be sunny, weather can be cloudy. I mean rainy. I mean rainy. Okay. So, and then here is umbrella and no umbrella. So if there is sunny and there is umbrella, and that is a probability of 0.2. Sunny and no umbrella, probability of 0.8. Some people must be cautious, or like maybe thought it could be rainy, or maybe there are different types of umbrella. And then rainy umbrella chance is 0.9, and then rainy no umbrella is 0.1. Maybe rain came after they left, right? So now we are going to use the sensor Markov assumption. It is same as Markov assumption. Now the sensor Markov assumption is the assumption that the evidence variable depends on the corresponding state. I know I was saying same, but it is seem it may seem a little different. But yeah, it is on the corresponding state only. So that is the sensor model assumption. Oh, I understand. Yeah. Let me draw a Markov chain for you with hidden variables. You guys liking the session, guys? What can systems do? We will discuss them in a minute. And then there's this. For not making it complicated and easy to understand, this is my umbrella. And if that umbrella is filled with black, that means no umbrella. Okay? No umbrella. And if it is empty, then it equals umbrella. Okay? Because I'm not here coloring umbrellas, right? So this is the Markov chain, as you saw, like sunny, rainy, and then again rainy. This is x0, x1, x2, x3. Now we have some hidden observations going side by side, like this. We are reading umbrella signs now. Umbrella signs. This one is colored filled, so no umbrella this day. Many people were cautious this day. They brought umbrella, and then it was rainy, so they have brought umbrella. So so this is how a hidden Markov model looks like. See, this is connected. This, all of them are connected, right? Not, and it is only connected to its corresponding state, not to any other state, right? Makes sense, guys? Now let us get into what Markov models can do. And if first another thing here. Hidden Markov code, yeah, I want to get into that. Yeah. What can hidden Markov model do? We're going to discuss 5 things. There were 5 things. 4 things actually, sorry. 4 things. Let me check. There's filtering, there's prediction, there is smoothing, and most likely prediction. Okay. There are 4 things. So, what is filtering? Given observation given observation from start until now, calculate the distribution from current state. Given observation up to now, compute the probability distribution from the current state. Example, is it raining right now? Okay, for now. And then we have got prediction. Given observation from start until now, calculate distribution for the future state. That is what we were doing, right? For tomorrow. Filtering today, prediction tomorrow. Smoothing. given observation from start until now, calculated calculate distribution for past state, like something in between is we they we lost the data in between, right? We got the data for day 1, we got the data for day 3, we got the data for day 4, but we do not have a data for day 2. So we can predict for day 2, and that prediction for filling up that graph is smoothing. Your observation up to now computes probability distribution for that past state. Did it rain yesterday like that? Yeah. Then the most likely explanation, uh, given observation from start until now, calculate most likely sequence of states. Like uh, like we did, like rainy, sunny, sunny, rainy, 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 sunny, sunny, rainy, sunny, 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 like that, like 50 days. Even can be for the hidden states also. Here it is here it is written infer the most likely sequence of hidden states from observation. Okay, this is for hidden Markov model. I got into Markov model. For hidden Markov model, we can generate states for uh, umbrella, not umbrella, 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 not umbrella, not umbrella, umbrella, not umbrella, like that. Yeah. Also used in voice recognition, record audio. Okay. So this is the hidden Markov model code. So we are again using pomegranate. We got sun, the discrete distribution. Then we got the rain, discrete distribution, and then we got the states. We have given it the two components. Then the sensor model is there, and the distribution, and the transition model is there. And then we are going to start with a 50-50 probability, and then we are going, and then we want a state name sun, or it will be sun or rainy later, right? So uh, for matrix, take the transition matrix, observation distribution, and start probabilities. State name labels, hidden states, call model is just what is there. Very simple code. This is right. Then we got the HM prediction, most likely explanation one. We got code, we got observation, that we have umbrella, umbrella, no umbrella, 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 no umbrella, no umbrella. Now we want to predict, from the observation we want to know the real thing which happened, it was sunny or rainy. So based on the observation given, like it has given rain, rain, sun, rain, 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 sun, sun. So umbrella observation suggests rain, no umbrella suggests sun. The model infer a sunny break on sunny break on day 3 and 2 sunny days at the end, consistent with the sensor model. We have given sensor model here only. We are talking about this only, right? And then let's get into lecture summary. But today I got a unique way of a lecture summary. I'm not going to use this, right? Uh, you guys getting along, right? Now let me get to mind maps. We are going to use mind maps, right? We are going to use mind maps. Here it is. Sorry. Uh, hmm. So let me close this. Yeah, I got this here, right? I don't know why it is not close opening. So I will now explain you guys this. Let me check if this is the correct one. Yeah, this is the correct one. So oh shit, man. I don't know what is happening. I think I actually understood what is happening. Okay, so uncertainty of AI we learned first, probability basics, in which we learned possible world and axioms types. We learned world and then probability of that world. Then we learned the axioms, the boundary range 0, 1, sum to 1, and then we learned the types. They are unconditional, conditional. That is the probability of A given B, and then there is joint probability. Let us close all this. Right, now let us get into core probability rules. We learned 4 rules, I guess today, 5 rules. Okay, negation, inclusion, exclusion, marginalization, conditioning, and base rules. Base rule was very important. Then we learned about Bayesian networks. What are Bayesian networks? We learned the structure, the inference, and the sampling techniques. The structure was that it is a directed graph in which random variable nodes are connected, and it has dependency edges, and the top node is like the parent of the parent, the top node which has no node connected to it. It is independent. Then the inference we learned, it can be done through enumeration, exact, and then sampling, approximate, right? And then we learned polynomial sampling too, and then we got rejection sampling and likelihood weighting, right? After uncertainty after Bayesian network, we got into Markov model because we were into uncertainty of time, to go over time, right? Markov model, we learned Markov chains, the hidden Markov model, and what can hidden Markov model do. In Markov chain, we learned about Markov assumption and the transition model. Markov assumption was, of course, the it was based on finite number of previous states, right? And the transition model is the joint distribution table, and then the hidden Markov model. The hidden Markov model gives the hidden states observation, the sensor model, right? We learn all those. The observation, through observation we can learn about the real day, what happened, the hidden states, and through the hidden states we can learn about the observations. We know the code, we have written the code for all of them, and then we know the HMM tasks. We learn about filtering, prediction, smoothing, and most likely explanation, right? Filtering I told you, prediction I told you. Oh shit, man. Yeah, where was I? Yeah, Markov models. Yeah, Markov chains I told you, HMM I told you, right? So this is over. And then implementation through pomegranate, this is the code part. Discrete distribution was there, in which there was no dependency, and a conditional probability table in which there was conditional, the nodes were connected, the Bayesian network. And then model breaking, we learned the sampling and all, right? This was the mind map. And then in the lecture summary, we can also see the probability rules, the conditional probability, random variables, we learned joint probability, Bayes rule, probability rules, Bayesian networks, sampling to Markov model, hidden Markov model. Uh, I hope today's lecture was very fruitful for you guys. Uh, because we learned so many new things today, and we have crossed the 2 hour mark also, right? We have on 2 hours 7 minutes, right? So we are at the end of the session. The summary is done. Tomorrow we also have a live session, and if you guys which are currently watching, if you guys want to know the next topic is optimization. So I don't think that is that much hard topic. It is actually much harder to explain than it is to understand actually. Yeah. I will explain that in a very layman language. It is very easy, right? So if you want tomorrow's session, tomorrow we are available from 3:30. I guess tomorrow will also take 2 hours, near 2 hours, for 40 minutes is my prediction. So today's session was very fruitful for you guys. I think so. It is a very important topic. All large language models use that. Tomorrow's optimization, you may see think that it is not that important, but it is actually very important too. All of the topics are very important, and don't forget to come back tomorrow. Leave a like and share. I'm going to end stream now, guys, and see you guys tomorrow. Subscribe to Knowledge Culture. Come back, and also check out Generative AI course, and also our past lectures on knowledge and search algorithms. If you guys came late, you can check the full session, right, from the start after this is processed, right? See you tomorrow, guys. Bye, guys. uh, I like to say bye to the chat and thank you for supporting us, guys. See you tomorrow. No problem.